Have you ever looked up at a skyscraper and said, how tall can this really go? Well, I'm about to climb up there to show you something.
Until 1971, this was the tallest building in the world. After that, for decades, buildings got taller and taller until the Burj Khalifa was built in Dubai. That's now the world's tallest, and it's twice as tall as the Empire State Building. And soon, a tower will open in Jeddah, Saudi Arabia, that's 3 times as tall.
Frank Lloyd Wright said a mile-high tower is technically possible, and he designed one back in the 1950s. I spoke with the people behind the tallest towers ever, and they told me exactly how far we can push it.
I think Jeddah Tower is the next step. I don't think that it's the limit of how tall we can go. The sky's the limit.
We went into the hidden parts of the world's super talls.
I wanted to show you guys what it feels like to be at the top of the world.
To answer the question, how tall can we actually build? Who pays for it? And is it even worth it to keep building higher and higher?
And what did we find out? The higher the build, the stranger things get.
So the first thing you need to know is that there's not one single right way to build a skyscraper. From the steel frame inside of the Empire State Building to the more modern outrigger system that's inside One World Trade.
We look at these structural systems we create for tall buildings as like different species, different animals, that work at different scales. But unlike nature, we don't need to evolve from one to another. We can create completely new systems. It's not really derivative from something before or evolving for something before.
Up until the Burj, all of these buildings had something in common, a single tall support. You could add what's called outriggers, which were mechanisms to connect the outer walls to that central concrete structure. But there's one way that you can add support to a super tall that's very simple. The breakthrough of the Burj Khalifa was this 3-part design that unlocked a new era of super tall structures.
We created this new species, this new system, and then we gave it a name. We called it the Buttressed Core.
This buttressed core allowed the Burj Khalifa to dwarf everything before it. It's 828 meters tall, and while the record for the world's tallest building is usually beat by incremental jumps, the Burj Khalifa was over 60% taller than anything else built before it, and nothing completed since has even come close.
The tripod form is extremely efficient. So think of it as a 3-legged stool. When you have 4 on a stool, if one's kind of a little off, you kind of feel it rock, but 3 is very efficient.
The wing-like design also reduces the need for materials that were used to build earlier skyscrapers.
There's actually more steel inside the Empire State Building than there is in the Burj Khalifa.
So what's it actually like to go up the world's tallest building? Well, we sent a producer there to find out.
Thanks, Dan. I'm going to show you the full experience of at the very top of the Burj Khalifa. It's humongous, it's gigantic, and it's surrounded by all kinds of tall skyscrapers, but it exactly dominates them. I can't even capture it in a horizontal format in the widest of the lenses. You can see that.
The first thing to note is that the experience of going to the top of the Burj begins long before you even reach the building. You have to walk through the massive Dubai Mall just to get to where the line starts. It turns out that going to the top of the Burj demands endurance. The total cost of a trip like this with the VIP ticket, getting there, and souvenirs would probably run about $500.
I'm embracing this view. This is what human admiration and vision can lead to. I can see the infinity from here.
Our producer may have enjoyed his trip, but it got me wondering, are these incredible feats of human engineering just expensive tourist traps? Well, look at the numbers. The Burj could be raking in as much as $700 million a year from over 9 million visitors. That's twice the amount tourists spend to visit the Empire State Building and Eiffel Tower combined. One way to think about it is that the Burj made back its $1.5 billion construction costs in just 3 years of tourism revenue. It could be worth it to build tall just to stick a gift shop on top. The buttressed core has gotten us higher than ever before, and a similar design is being used in the Kingdom Tower in Jeddah, Saudi Arabia. However, it might not be the right form for a mile-high skyscraper.
I think there's a limit to how high this structural system is appropriate. Is it, certainly a kilometer, maybe 1.2 kilometers. At a certain point, you have to create a new species, a new animal, a new structural system that go that high.
That's exactly what Bill's team did. Later, you'll see their design for a structure 10 times the Eiffel Tower that overcomes all of the limits of height but looks nothing like the Burj or the Kingdom Tower. But first, let's look at why the Burj itself broke with symmetry and why that lopsided look is one key to going higher.
Tell me, where are we at, Bill? What's going on here?
Okay, I'm here with Brad Young, who runs the wind tunnel here at the SOM. Brad and company spent like months and months calibrating this wind tunnel so that it accurately represents the velocity profile of wind that you see in the real world. What we use here is good German, very expensive styrofoam, okay? Because the model needs to be very stiff, but very lightweight. Okay, so Brad's firing up the wind tunnel. You'll see that there's a series of 6 fans at the end of the tunnel. All right, here it is. It's starting to fire up. And what the wind tunnel does, it shapes the wind profile that matches what you see in nature.
The secret to this carefully calibrated wind tunnel? Lego bricks. They're used to simulate how trees and buildings can affect airflow.
So we use computational fluid dynamics. That gives us a little bit of a better graphical understanding of what's happening and allows us to understand, why some of the changes we're making to the building may have the effect that we measure but we can't see. So this is a computational simulation of what you're seeing in the tunnel.
That computation is showing one of the key things that makes building super tall so difficult. They're called vortices.
So imagine you have a kind of a round shape and the wind is blowing towards you. On the other side of the building, there's kind of this vacuum that happens, and then as the wind vortexes come through each side alternately, they create kind of like a mini tornado that pulls on the building, and that can be really dangerous, especially if the building starts to move at its own frequency.
And this frequency is the key thing to watch for. If the timing of this wind syncs up wrong, this force can multiply. You see this most often with bridges. The Tacoma Narrows Bridge, known as Galloping Gertie, had a resonance that almost exactly matched the wind speed, causing it to bend and twist in the wind until eventually it collapsed. So there's one key focus for super tall buildings: confuse the wind.
As the wind hits the body of the building and organizes the vortices on either side, it can begin to rack the building from side to side, and so we want to disturb that. And so we're confusing the wind at every chance we get. The wind design is the governing factor on the super tall.
But there are a lot of different approaches to that.
Now, often what we're doing is using texture or form to confuse the wind to alleviate that behavior. But sometimes we actually accept the wind. And we've done projects where we've actually brought the wind through the body of the building, for example, or utilize spaces to ventilate the building, just like you would in a jet or in a high-performance car.
Right here, 432 Park, you can see that there's empty floors on it. They're called jump floors, and they're meant to let the wind pass through to cut down on the shear forces on the building, but there's actually nothing on those floors. It's just empty. And it also makes the upper floors even more expensive because they're even higher up.
But despite the intricate work that goes into the structural engineering of a super tall building, not everything can get worked out in a computer program.
It's quite surprising, but minor changes in the shape of the building can make dramatic changes in the forces in the building.
The Burj Khalifa was essentially reversed completely after wind tunnel testing. The spiral originally went up clockwise, but was changed to counterclockwise because of these real-life results.
And the data we got back was not good, okay? The forces were too large, the motions were too large. And so it's kind of a little bit ironic that if the first shape and structural system had worked well, we might have stopped there. But because it didn't, we had to make enough changes that we could then actually go much higher. And the building changed in height by 300 meters. It's 300 meters taller than when we started, which is essentially the height of the Eiffel Tower.
And there's one more trick that more modern skyscrapers have to survive the wind that's actually inside the building.
Did we do that? that wasn't awesome. Okay. We're going up a staircase from the summit where tourists are allowed to go. There's extra steps up. Ed, what floor is this technically?
That's 93, this is 94.
93
to 94.
Got it.
At the top of some of these buildings are hidden monoliths, super heavy objects tuned precisely like a musical instrument.
It's called a tuned mass damper, and it basically acts like a super heavy pendulum that offsets the wind forces on the building and makes it so that the people who are at the upper floors don't feel that sway at the top. Every tuned mass damper is different because it's calculated to the size and structure of the building. In Taipei, the Taipei Tower has a beautiful sphere that's sort of a sculptural element that visitors to the building can go look at. In Shanghai, the tuned mass damper uses electromagnets to modify how it works. All right, so now we're gonna go inside to see the TMD at the top of One Vanderbilt, which is the 4th tallest building in New York City. Let's go.
Do you remember how much it weighs?
Yeah, it's 500 tons.
Wow.
About 1 million pounds.
When you're doing the calculations for something, putting like something like this in a building, what are the factors that you have to account for to make sure that you're getting this the right size and positioning?
The classic example is the wine glass. If you take a good crystal wine glass and you flick it, you could hear it, right?
Right. It has a certain pitch to it.
It's just like that wine glass, every building has a resonant frequency.
Right.
Which we can calculate. We're designed for 110 mile an hour wind and a hurricane actually hitting Manhattan.
Right, like a direct hit hurricane.
A direct hit hurricane. Yeah, I don't think that building twice as tall as this is going to be an issue in the next 10 years.
You heard it here first.
Assuming somebody wants to pay for it and actually has a use for a building that tall.
But here's the thing about TMDs. The Burj Khalifa doesn't have one. That's because it has a buttressed core design, it has concrete at higher floors, and the way it's designed to confuse the wind, it doesn't really need one. If we're gonna build a mile-high skyscraper, we're probably gonna need a TMD, or maybe more than one depending on how high up it goes.
Let's be clear, all these measures have less to do with preventing the worst case scenario of a building collapse, and a lot more to do with the comfort of people who are going to be living and working at the highest floors. And as you could see, mitigating those factors can get very, very expensive. But what if no one needs to go that high up in a building?
One of the cheat codes to adding height onto a building is to add a spire. Just look at the Chrysler Building. The architects of that built a spire inside secretly as it was in competition with other skyscrapers at the time to become the tallest. And in the last months of construction, they shot the spire up and got the world record. That was until the Empire State Building was built. But a spire is an easy way to add height onto a building. And on the Burj, the spire is actually 244 meters tall, which means that 30% of the structure is not meant for regular visitors at all. The only people that are allowed to go up there are technicians who have to change a battery on this specific device that attracts lightning bolts, and a few lucky celebrities. That means the spire on the Burj Khalifa alone would be the 11th tallest building in Europe. But if we're only trying to go as tall as possible, why not just build one giant uninhabited spire? If you broaden the definition of the world's tallest building to the world's tallest human-made structure, things start to look a lot different. 45 out of the top 50 tallest structures of all time are not buildings at all. And to show you what I'm talking about, we're going on a little road trip. We're about 15 or 20 minutes outside Hartford, Connecticut right now, and we are approaching our final destination. Oh, wow, I can see it now. That's why we're here. The tower that we're going to see, the WTIC or WHPX, which is the later call sign for the tower, is over 400 meters tall. That makes it taller than the Empire State Building, but it's not even close to being one of the tallest masts in the world.
The tallest radio tower was actually the Warsaw radio mast, which was built in Poland in 1974. And the signal from the mast could be heard as far away as the US and Canada. But here's the thing about these towers. They're built for maximum height with the smallest footprint possible. And when you're talking about a steel tower that just goes straight up and down, well, you need something to tie it down. This is the anchor for a guy line that you can see goes from there all the way up to the tower. And each of these lines is kind of like a finger trap. The more you pull on it, the tighter it gets. But if one of them fails, it could be catastrophic. In 1991, during much needed maintenance on the Warsaw Tower, the main guy line got disconnected and a gust of wind came and twisted the structure and the entire thing collapsed. The tallest structure in the world had collapsed and miraculously no one was hurt, but it wasn't a one-off. Made it to the top, there's a few guys working. I'm making a video about like tall structures, so I'm just taking a video of the tower. I'm just gonna take one quick shot just to show the bottom, because I think a lot of people don't realize that these things end in a sort of a, that it looks like really unstable, right? Okay, so we found out where we're not allowed to get this close, but there's a facility here and there's guy lines in every direction holding this thing up. There have been at least 9 collapses of towers like this over 600 meters. And that's because the guy lines and the way it's set up are so fragile that if you lose the support of one of them, the tension in one of them, the thing will twist and come crashing to the ground. Antennas like these almost always top out at around 2,000 feet. And that's because any higher than that, and they start to pose a risk to aircraft, particularly small aircraft. But there's no reason that you couldn't build something like this to surpass the Burj Khalifa, and for a fraction of the cost and material. Something like this is super cheap. It cost about $500,000 and only took 30 days to build some of the tallest masts of all time. Now, do you remember at the beginning of the video when I mentioned the super tall structure that was designed by the engineer behind the Burj Khalifa? Well, Bill Baker thinks an uninhabited structure that goes straight up and down could easily hit 3,000 meters, which is well above our 1 mile limit.
The Eiffel Tower was originally called the 300-meter tower. If you look at the drawings, that's what it says, in French, of course. And so we thought, well, okay, that was, 1889. Here we are in the 21st century. How about let's go 10 times as high, 3,000 meters, okay?
That's way over 1 mile high. In fact, it's almost 2 miles. If you put that next to the Burj, you can see how tall it really is.
It behaves very well in the wind, both because of the shape and also because of the porosity. As it goes up, eventually it becomes so dense that we have to make it sparse again and stop some of the pattern, and then it gets sparse again and eventually becomes solid at the very tip.
Structures like these work well against the wind because it's essentially hollow. The wind just kind of passes through, adding glass and floors and concrete and places for people to live, and the whole thing stops working. Man, Prakar got to go up to the top of the Burj Khalifa, and I had to climb up Rattlesnake Mountain to go look at a broadcast tower. That's not fair. That's not fair.
Bill's reboot of the Eiffel Tower looks more like a broadcast mast than it does like a functional skyscraper. There are no apartments, there are no offices. It's actually designed to be a vertical farm and tourist attraction. That made me wonder, how do we define what a building actually is? Couldn't we have a few people living on the lower floors and just stick an antenna on top?
Oh, you've stepped on the third rail, my friend.
That's Daniel Safarik from the Council on Tall Buildings and Urban Habitat. They're the ones who make the rules on how to measure the world's tallest buildings.
So the short answer is no, we don't count the antenna in the ultimate ranking height of the building. We have 3 different types of criteria. There's height to tip, which is the absolute tallest thing on the building at any point in time. The problem with using that as your ultimate height determinant is that it often changes. So it's very likely to be replaced or superseded by a different kind of technology several times over the lifetime of that building.
Take Chicago's Sears Tower, now called the Willis Tower, and Kuala Lumpur's Petronas Towers. Even though the Petronas pair took the title of the world's tallest in 1998, the very tip of the Sears Tower actually stands almost 100 meters higher.
The things on top of the Sears/Willis Tower are antennae, and they have been different heights, significantly different heights over the years. Whereas the spires, permanent architecturally designed fixtures on the top of the Petronas towers and others like it, have stayed the same. The so-called architectural height, which is the second criteria, outstrips the other two. The third one is, of course, the highest occupied floor.
And according to the council, to be considered a building, people must be able to occupy at least half the floors. So for our mile-high structure to actually be counted as a building, we could have 800 meters of habitable space, followed by almost 800 meters of spire alone. So let's recap. We know we're going to need a new structural system, rigorous wind testing, maybe a tuned mass damper at the top, and almost 50% of the building can be a spire. But what would something like this actually be made of? Once you've designed a mile-high building, the actual work has only just started, and the first step is a strong foundation. It's not just about digging deeper, but finding the right location.
What's interesting about tall buildings is that a lot of times they're building, in cities, okay? And where are the cities? A lot of times they're in river valleys, where there's ports, and a lot of times they're places where there's really terrible soil, and so that's not unusual.
The record for the deepest foundations for a skyscraper goes to the Petronas Towers in Malaysia. The building site actually had to be moved about 60 meters to make sure it was sitting on the right kind of rock. 104 concrete piles supporting it stretch up to 114 meters, or 374 feet deep. That means 25% of the structure's height is buried deep underground. The strength of concrete has been a big limiting factor for building high, but materials have come a long way. Concrete especially has changed dramatically since the 1950s.
It's almost 10, 20, 30 times stronger than then. And why is that? There's been a lot of innovation in the material. One such innovation is called a superplasticizer that helps reduce the amount of water that goes into concrete. So now we're talking about ultra high performance concrete that can really support, theoretically support a mile if it's thick enough.
And these concrete developments were crucial when building the Burj.
So one of the innovations was an extremely high pressure pump. So it can pump it really high up. And it's pretty important that this is done very quickly because, concrete cures.
Due to the heat of the desert, this concrete could only be pumped at night too, and it had to be filled with chips of ice to stop it setting too fast.
Pretty interesting to realize that, all these small niche things are actually really what is making these things possible.
And what feel like niche problems are going to be the real sticking point when building super tall. Building a mile-high skyscraper in the heat of the Middle East will have entirely different challenges to doing the same in cooler climates. Every expert I talked to said that we can build taller, but each time there's going to be more and more crucial considerations and less room for error. Just take the kilometer-high Jeddah Tower currently under construction.
So the logistics or strategy around getting that concrete up to over a kilometer is part of the design challenge. That needs to be extremely well coordinated because you're not going to go back in and alter the concrete during construction to solve your problem. We often kind of embed in our guys that, on these projects, when you make an error, you can multiply that error by 1,000 times across the scale of this building.
It's extremely expensive to retrofit a building once it's already up. Look at the Empire State Building. The owner spent $1 billion modernizing it over the last few decades. What most people don't know is that skyscrapers are only designed to last about a century.
The average age of the 200-meter building that, when it is being considered for demolition, according to our research, is around 41 years, which is pretty pathetic.
What happens to buildings like the Burj Khalifa 100 years from now when they get too costly to maintain? Is it simply left to crumble or pulled down at a much larger expense? That's why Gill's firm made sure to use the best-in-class vendors for everything on their upcoming project.
When we first started this project, We went out and interviewed the best elevator consultants in the world, the top 5. We did top 5 mechanical engineers in the world, the top 5 plumbing engineers in the world, structural engineers, because we knew we were on a path of doing something that hadn't been done before. And so we learned a lot about the systems. Now remember, over 14 years, you can imagine that those things change.
Those elevator consultants he mentioned, they're especially important. It seems like the structural issues might be the biggest limiter for a super tall, but it's actually elevator technology that still needs to catch up.
If you're in an 800-meter tall skyscraper, no one is going to want to take the stairs. So that's why elevators are probably the most important technology inside of a super tall. In a 500-meter elevator shaft, there could be something like 27,000 kilograms of steel rope. And the reason there's a limit of 500 meters for an elevator is because after that point, the elevator can't support the weight of the rope anymore.
The solution so far to this 500-meter limit is to have multiple elevators and sky lobbies where passengers can change between them. But this takes up a huge amount of space. And if there was a mile-high building, changing elevators twice or more to get to your apartment is going to be frustrating for anybody living at the top. This 500-meter limit looks like it's been broken by something called ultra rope. It's an elevator rope made from carbon fiber, and it'll be used in the Jeddah Tower. This would allow elevators to go up to 1 kilometer high, but if we want to reach even higher than that, we'll need newer technologies again. Frank Lloyd Wright was actually one of the first to consider a mile-high building when he drew up the Illinois, a 528-story tower with parking for 100 helicopters. He was using a tripod-like design, way before anyone else had considered it. But the most outlandish part of his design was actually the elevators. The plan was to have 76 5-story high elevators that could travel a mile per minute and be atomic powered. These would be mounted on rails, kind of like vertical trains. And here's the thing, once the elevator challenge gets solved, designs can veer into the fantastical.
If we are beginning to, fly cars or vehicles or drones into the building, if we're beginning to advance technologies for elevatoring that can move sideways or can run on rails, the sky's the limit.
Imagined in the 1990s, the Exceed 4000 is a 4-kilometer tall behemoth that would loom over Tokyo's Mount Fuji and be able to house 1 million people. But even the director of the firm behind it said it wasn't meant to ever be built. The tallest structure ever proposed by architects is the Tokyo Tower of Babel. It looks similar to Exceed, but it more than doubles the height to 10 kilometers. It was designed to house nearly the entire population of the city of Tokyo.
You could go probably 9,000 meters, height of a mountain, like the Mount Everest. At some point, it'll just take so long to build you won't ever get there, and so it may never get completed. The limit is going to be set by time as much as any time and political will, and financial resources.
The Tower of Babel would cost 3 quadrillion yen, or $22 trillion. That's 14,500 Burj Khalifas, so basically a made-up amount of money. And yes, you may have seen photos of an elevator to space or an orbital ring that surrounds the entire planet. Structures so high they push out of the atmosphere. Those might be impossible, but the reasons why are the subject for a completely different video. So more than wind, materials, and technology, it turns out that the real limit will always boil down to the bottom line. The top 3 tallest buildings in the world cost an average of $2.6 million per vertical meter. There are so many reasons not to build tall, and developers can make money just building regular height buildings. But these projects are about so much more than economics. They're about putting your city on the world stage.
The purpose of a tall building is interesting. I think a good example is the Eiffel Tower. It's not really a building, it's a restaurant, it's an observation tower. But it's a placemaker. It tells you we're here. You can't imagine Paris today without the Eiffel Tower, or France, or Europe, or the world. If you're in a country or a city which has a lot of ambition and you're highly optimistic, a distinctive, good, tall building is one way to do it, you know, to kind of plant your flag, you know.
When I first started this story, I have to admit, I was skeptical that buildings could get much taller. But now that I've talked to the people building them, the question of a mile-high tower isn't if, it's a matter of when. And I guess the question is, how much would you be willing to pay to buy a ticket to go to the top?